some interesting things around Z transforms. And one of the things I often hear people say is like, okay, so basic Z transforms, there aren't a whole lot of really interesting things there. And I think when students start off looking at this, the Z transform feels pretty simple compared to other things, particularly because you primarily focus on FIR type systems. And fair enough, because it actually really helps you sort of just get the concepts in a good place, and that's really important. But it turns out there's a whole bunch of very interesting transforms, and particularly if you're familiar with other kinds of transform theory, like Laplace transform or Fourier, you begin to understand that there's actually some really fairly deep concepts there. And the one that usually almost always gets brought up is talking about, okay, imagine if I have a step function in my sample domain, and I'm talking about having basically some sort of series, power series, which is kind of an approximation of an exponential decay or expansion, depending what you're doing. And you get this kind of transform in Z, which kind of makes sense given you have an infinite series you're summing up. So it's a very familiar form. And usually a lot of times you just kind of stop here. You're like, okay, we're done. There's not too many other things there. And I'm like, well, wait a minute, there's some other things. And I want to bring in the fact there's a whole range of things you can do with sinusoidal functions, which show up all the time. Like I'm going to have a step function that starts a sinusoid. Like, what's that going to look like? We might know what the frequency response ends with, but you don't actually know what it starts with. And so what's the transient? What's the behaviors? On and on and on it goes, right? And you'd like to be able to have this kind of information. Well, I want to say if you took this known transform and you say, well, instead of A, and A is a complex number. It's not usually talked about that way when you first introduce this because that just feels a little bit more stressful, but A can be complex. Okay, what's a complex number? Well, e to the j omega 1 is a complex number, and I can raise that to the power n. To which we know that's a sinusoid. Fair enough. But it turns out if I take this structure, then I just basically put that value into next to the z minus 1 term, and you think, well, that's an interesting way to talk about a transform of a sinusoidal signal with a step and converting it into a z transform. You think, wait, if I can do that, I bet I can do this for cosine, which is just then the sum of the two. Or I could do it for sine, which is the difference of the two. Remember your 1 over 2j. And it turns out it works out, you can actually get a nice function out of it. You get a function that's 1/2 times all of these other terms, but times basically one of these for the positive and the minus term. Well, cross multiplying this together, I get 1 minus cosine omega 1/2 z to the minus 1 over the second order term, which isn't surprising, and particularly if you're used to looking at this in other transform spaces, you'd see the same, you'd expect a second order kind of thing happening here. So this is quite cool, right? You might imagine having double roots and so forth. A similar thing happens for sine. Now it actually just has the z minus 1, and it has has that same denominator term. You think, wait a minute, if that works, what happens if I put a sub n in front of it? So now it's an oscillatory sequence that's now going down towards, say, converging towards 0. Very, very typical thing. Kind of gives you this sort of general exponential, real and complex kind of function that we're often used to using. Well, again, same sort of thing. Two terms cross multiply, and I get this 1 minus a to the cosine omega 1 z to the minus 1. And you're like, this is getting interesting. Similar term happens for sine, but now I've got the a's in these two places. Other than that, it looks exactly the kind of form you had here. These are all very, very reasonable forms. It's wonderful to have a second order term because I may have a z transform where I've got some second order terms that I don't really want to factor, and it looks like this form. I might want to use that. But even more interesting is you get cosine and sine. There's one I kind of like to think about, which is the blur between the two, which happens a sub n cosine omega 1n plus theta, where theta is now a phase shift. Now this is kind of interesting because if I have a phase shift in this, A whole bunch of things I can do here, right? So, in fact, if I have a phase shift of 90 degrees, it gives me the sine one, and I would get something that will look pretty much the same function again. If I get a phase shift of 0, I get exactly this function back again. But I can work through all of this. Why would I want an intermediate phase shift? Usually the case is when I'm trying to do, say, match this to actual input conditions, match things in, I might have a particular functional form that comes out of z transforming something in some transfer function and pull it together. I might get a case where I get a very particular combination of things, which you might imagine as a combination of this numerator and this numerator. Well, the combination of a cosine and sine is a cosine with a phase shift. So let's just think about it from a phase shift perspective. And that turns out to give me a very, very useful term here. One fun case, and this is a really useful one, if I wanted to have something without a delay term, then if omega 1 hat minus theta is pi over 2, this term disappears, and I'm left with just sort of a cosine over this. Now, interestingly enough, that can happen at pi over 2 and minus pi over 2. So two possible solutions. So I always need to double check what makes sense given my initial starting points and my initial conditions. But a very, very powerful thing. And in general, when you normally think you don't have Z transforms to kind of help you out with some of these very harder problems, it turns out you do, and there's a lot of really good insight and instinct in behind all of this.